So this thing should be kept in mind that loads are always connected to the phase. Okay, so if the supply system is not balanced, then what will happen that one of the phase might get to 30 volts and other might get to 40 volts. So there will be an unbalanced situation. Okay, so to avoid this, the supply system is always balanced, but at the load end, the load, three phase load can be balanced, it cannot be balanced. Okay, it is quite possible that the same load is connected to all the three phases, but it is also possible that most of the cases in household system and or the distribution system, what happens that the load is not balanced. Okay, because we might connect different types of loads or different ratings at different point of time. Okay, so how to identify whether the supply system is balanced or not? So we have to check out for two things. First is the magnitude and other is the phase angle. Okay, so say if the voltage is 100 volts. Okay, so and the three phases are say ABC. Okay, so when we are representing the voltage or the EMF, first thing which is to be kept in mind is that during phasor representation, the physical quantities are represented for RMS values. Okay, this thing is common with single phase knowledge as well. Okay, so this is, you can say this is A, this is B, this is C. Okay, so in the 2 marks type of question, what can be asked? Phase sequence can be asked. Okay, so if the phase sequence is asked, then what care we have to take? Since the supply system is balanced, so if the magnitude is 100 volts, okay, and for our convenience, we have, for initial stage, we have marked 0 degree, or you can say that the A phase voltage is in line with the x-axis. Okay, so if the B phase voltage is having same 100 volts and the angle is minus 120, similarly C is having 100 and angle minus 240 or 120, all the same, because we can always add 360 degrees or subtract 360 degrees as per our convenience, and it will make no difference to the results. Okay, if the situation is like this, so we can say that the phase sequence is ABC. Okay, because when we are following the positive direction of x-axis or in the anti-clockwise direction as shown here, so zero crossing will take place first by the A phasor, then by the B phasor, then by the C phasor. Okay, so this might happen. Okay, second case can be if this is B and this is C, or you can say if B and C are interchanged, then the phase sequence will be ACB. Okay, So this is our simplest case. Now we can add a bit complexities in it. So how can we add complexities? We have to identify that the angle difference is 120 degrees. Okay. So it is quite possible that, say, this A phase is having 100 magnitude and 60 degrees as angle. Okay. So if it is having 60 degrees and this is A, and we are assuming that the phase sequence is ABC, then the phasor B will have 100 and angle will be angle A minus 120 degrees. So 60 minus 120 degrees, that will become minus 60 degrees. And similarly, the C will be minus 180 degrees. Okay. So we should be aware that the angle difference should be 120 degrees irrespective of their angle at any particular instant. Okay. So in this numerical, we are having three voltages which is given by alternator. What is alternator? Alternator is nothing but the AC generator. Okay. So three phase voltages are given as 231 volts, 0 degree, and Y phase is minus 120 degrees and B phase is minus 240 or plus 120. So first of all, the phase sequence is clear as RYB. Okay. So next part is to calculate the line voltage. Okay. So line voltage in case of star connection system, as we have discussed in the theory class as well, that the line voltage is root 3 times phase voltage. Okay. So phase voltage is given to us, and when we calculate the line voltages, there are three line voltages as explained in the phasor diagram earlier in the previous class: RY, YB and BR. Okay. Again, it is noteworthy that the letters of the phase which you denote for line voltage representation sequence should not be disturbed. Okay. For example, RY is B is the phase sequence. So first line voltage will be R and Y, then it will be Y and B. If next phase sequence is this, then again it will be RYB. So next it will become B and R. Okay. So similarly, so since the phase voltage is same, supply system is balanced, so the line voltage will be same in magnitude. Okay. So 231 into root 3, 400 volts. Okay. So what is the word of caution here? Sometimes in the question itself, it is not clearly written whether we have to calculate the magnitude of the line voltage or the line voltage complete. What is complete? Means that since it is a vector quantity, so ideally these line voltages should be represented as magnitude followed by the angle. Okay, so phase angle of the angle of the line voltages can also be taken care of as explained in the phasor diagram. We have explained in the phasor diagram that if these two are phasors, inverse phases, if this is R phase and this is minus Y phase, and we have done the parallelogram of vector addition to get the ERY. So what will be the angle between the R phase and the line voltage? It is 30 degrees. Okay, so ideally it should be 400 volts, angle 30 degrees. Okay, similarly other phases can be resolved in terms of the angles. So let's move on to the next question. That whenever we are talking of the supply system, okay, as given here as 200 volts, so this is always line voltage and RMS value. Okay, this thing is to be kept in mind. It is not phase voltage, and load is always connected to phase. Okay, so if you are given say 10 ohm resistance or resistive load, and this is line voltage of 200 volts, and you are required to calculate the current flowing through the load. So what will you do? You first of all convert this line voltage into phase voltage, or 200 upon root 3. That will be its phase voltage. Then you will divide by 10 to get 20 upon root 3 amperes current. Okay, so firstly it is same, that line voltage is equal to root 3 times phase voltage. So in this question it is clearly written that phase voltage is 200 volts. Okay, so phase voltage is given, so we will multiply by 3 root 3 to get the line voltage. Okay, now its second part is that calculate the line voltage when one of the phase is reversed. Okay, so let us suppose that R phase is reversed, so ER now becomes minus ER, and minus ER becomes ER. Reversed, what do you mean by reversed? We mean that it is changed by 180 degrees. Okay, so this is the new situation as shown in the diagram. Okay, now we have to calculate the line voltage. Okay, so formula of line voltage remains same. It is ER minus EY. Okay, so ER minus EY. So since it is balanced system, so the magnitude of the phase voltages, here it is time and again you will see that it is represented as EMF. So the concept or the difference between the EMF and voltage is already explained to you in the previous unit, that if there is no drop, then we can assume that the EMF and voltage are same. Okay, so ERY is ER minus EY. This is our formula from the vector algebra. So now let us see what is happening. So magnitude ER and magnitude EY is EP. This is our ER vector and this is our minus EY vector. And ER minus EY, obviously, so it will have the resultant in between. And since the magnitude of the ER and EY or minus EY is same, so this line voltage will be the angle bisector. Okay. So if we draw, we will firstly use the trigonometry concept. So if we draw the perpendicular here, so this will become EP cos 60. This is our EP, hypotenuse, phase voltage magnitude. So cos theta or cos 60 is this base. Similarly, if we drop a perpendicular here, what will happen again? We have to calculate the same formula. EP cos 60 is along the line voltage. Okay. So EP cos 60, EP cos 60 is 2 EP cos 60 and cos 60 is half. So half and 2 will cancel out and it will be EP. Okay. So our answer is 200 volts. Now other line voltages. In the previous numerical, I have told you that when the system is balanced, the line voltages will be equal in magnitude and phase angle. Okay. But here one of the phase is reversed. So the line voltages will be different. Okay. Okay. So before moving further, I will also tell you how to calculate this magnitude using vector algebra. So ER square plus EY square. When we write this formula in terms of calculation of magnitude, what we write, in which manner we write. For example, in this case, we have to write like this: ERY vector sign mod sign, then we have to calculate. Again here it will be ER square plus EY square minus EY square. But since the phase values, magnitude of the phase value same, so we can write here as EP mod square plus, this can be minus EP vector square plus 2 EP minus EP vector. This is I am doing for first time, that all this mod and vector sign, but to save the time for the future, this practice will be avoided. Okay. So cos of the angle between them, so it is cos 120 degree, and we know that the cos 120 degree is minus half. Okay. So this is minus half. So this 2 and 2 cancel out, it becomes minus. So this is EP square, this is plus EP square, this is minus EP square. So it will cancel out, only this EP square remains and this square cancel out, and we get EP as the result. Okay, clear? So we have seen that using the magnitude formula from the vector algebra or using the trigonometric formula, we get the similar results. Okay. So same thing is to be done for other line voltages. Okay. Okay, now see to it next line voltage. Next line voltage is EYB. So it is EY minus EB. So again we can take the cost components. So angle between the line voltages and phase voltage here is 30 degrees. So 2 EP cos 30. So resolving that, we will get the value as 346.41 volts. Okay. Similarly, we can calculate the third line voltage as well, which is EBR. Okay.